Hi, I would like to discuss with you another type of occurrence with rational functions, and that is when you can get a hole in the graph of a rational function. So we've already talked about where vertical asymptotes occur, that is basically a vertical line through which the graph cannot cross, and as we approach that vertical asymptote from either side, the function values go off to either positive or negative infinity. Well, a hole in a graph comes from a value that makes the rational expression undefined, but the factor that that comes from can actually be reduced out. And I have it listed here as this. A hole in a graph occurs at x equals a if the function is not defined at x equals a, and if the factor x minus a is a common factor of the numerator and denominator of the rational function. So I have an example that I would like to walk through with you. It looks like any other rational function that we've worked with thus far. So let's talk about what we know just from this original form. Like if I asked you to find the domain or the asymptotes that you think might occur. Okay, so to find the domain we would have to think about where is the denominator equal to 0, right? So where is x squared plus 3x equal to 0? And that is where we get x times x plus 3 is equal to 0. So this is equal to 0 at x equals 0 and at negative 3. Okay, so our domain of this function would be from negative infinity to negative 3, union negative 3 to 0, union 0 to infinity. Okay? Now, if we use what we talked about before, we would think that we would have vertical asymptotes at the values where the denominator is equal to 0 at x equals 0 and x equals negative 3. But we'll come back to this one in just a minute. What about the horizontal asymptote? Yes, the degrees are the same, and so the horizontal asymptote comes from the ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. So that's 1 divided by 1, which is 1. So y is equal to 1. Now, I've graphed this function, entered it on my calculator. Remember to put numerator and denominator in parentheses. And look at the graph. We actually see that there is this vertical asymptote at x equals 0, right? But what's happening at x equals negative 3? Well, here's x equals negative 3. It's not a vertical asymptote there. But something unique does happen there. So x equals negative 3 is not an asymptote. And you're thinking, well, how am I going to know that? Well, that's because if we take a closer look at x squared minus 9 over x squared plus 3x, that can be reduced. And to reduce that, let me come over here. X squared minus 9 over x squared plus 3x is really equal to what? X plus 3 times x minus 3 all over x times x plus 3. So that factor where that value came from, that value of negative 3 came from, divides out, right? That x plus 3 divides out. And so that reduces them to x minus 3 over x. Okay? So we only have one vertical asymptote, and that is where this final function has a denominator equal to 0, which is at x equals 0. But understand the original function is still not defined for x equals negative 3, right? If we plugged in negative 3, we would still divide by 0. So something happens at negative 3, and what happens, this is where you have to be smarter than the calculator. There is really a hole in the graph at negative 3. In fact, if we plugged in negative 3 into this reduced function, negative 3 minus 3, let me do it here. We would get negative 3 minus 3 over negative 3, which is really a negative 6 over negative 3, which is 2. So at negative 3, 2, there is a hole in the graph. Your calculator can't show the hole because it lights up the pixels that are nearby. So there's really no way to do that except for the fact that we can investigate it further by looking at the table. So let me show you at the table. If we enter that function like I talked about, notice at -3 and 0 we have an error. So that means the function is not defined there. So we're either going to have a vertical asymptote or a hole. Well, how do we know which one we have? Well, you could certainly examine the graph for the vertical asymptote, but another way to do it, remember, a vertical asymptote is defined by what happens to the y values as x is approaching that value at the vertical asymptote. Well, notice what happens as x is going to 0 from the left and from the right. What's happening? Well, these y values are going to -infinity, right? But these y values are going to +infinity. So as x is approaching 0 from the right and left, y is going to plus or minus infinity. So that means that x equals 0 is indeed a vertical asymptote. Well, let's examine what's happening at the -3. So if I enter my table set up to start at -3 and then increment by 0.001, look what happens. Well, as we get closer and closer to the -3 from the right and from the left, what's happening to the y values? Yeah, they're getting closer and closer to 2. They're not going off to plus or minus infinity, so that tells us that we have a hole in the graph at the -3. Now, lastly, what is our horizontal asymptote? We can just confirm this. Remember, horizontal asymptote means what's happening as we go to plus or minus infinity. What's happening to the y values? Well, as x is going to plus or minus infinity, what's happening? Yeah, these values are going closer and closer to 1. So that means we have a horizontal asymptote at y is equal to 1. Okay? So remember where the holes come from. Holes come from values that make the original expression undefined, but then that factor is divided out. I'll leave you with a saying that I've heard my husband and a few other mathematicians say: you better know your asymptotes from your holes in the graph. Okay? So you guys take care, and if you have any questions, contact me.